Hi there, I'm playing with junk again. Or should I better say, I'm playing with vintage computers again. Well, I just got this huge suitcase here. And I'll show you the manufacturer logo just to confuse you, because it has absolutely nothing to do with what's inside. And I will show you what's inside right now. What we have here is an MMD-2 mini micro designer. That's a computer for education. It is extra built for schools and high schools and computer technicians, and it has attached an EID1, an experimental interface designer, and I will show you that in more detail. That's the MMD-2. It's manufactured by E&L Instruments Inc. Incorporated, and it consists of an Intel 8080 CPU. That's the one here. It has a couple of EEPROM sockets. Only one is occupied with the software that is necessary to make the keyboard and the display here working. I have two other ROM sockets here, which I'm not sure what they're doing. I haven't read the entire manual until now. Then we have three 8-bit I/O ports, or better output ports. It's only with LEDs here. We have an EEPROM programmer, which is not populated, so it was possible to program your own EEPROMs, or program your programs into the EEPROM to save it. There was also a serial interface, RS-232 or 20 milliampere. Depends which way you prefer to hook up your serial stuff, but that's also not populated. It has a cassette interface, which is also not on the board. So I think that's maybe a low-cost version, or it is a customized version for CDC, control data, because they used this entire thing, including the case, for their own in-house education of their technicians. And so they probably decided they don't need serial I/O and the programmer, but they added this module here, the experimental interface designer. And that's mostly a collection of all sorts of input-output interfaces you probably can have on a computer. We have a analog to digital converter, nicely labeled with all the addresses that you need for programming this thing. Then digital to analog converter, that's the part here. Then we have an analog meter, which is connected to the DA converter. We also have a motor that we can use to visualize all kinds of things. For example, it turns faster when the voltage here gets higher, and all sorts of stuff. Then we have another output port with 8 LEDs. We have a digital input port with external connectors, or we can use that switch to input any kind of data. Then we have all kinds of analog inputs. Let's move the light a little bit. Okay. We have a potentiometer for analog values. We have a light sensor here. You can program stuff to be light sensitive. There is a switch to switch the motor on or off if you need them or not. There's a temperature sensor. I think it's just a transistor. Yes, they even labeled it. It's a transistor that they use as a temperature sensor. And here is a selector switch where you can select what sensor you want to use. Temperature, light, potentiometer, or externally. You can also hook up an external source of, well, whatever, voltage up to 5 volt or something like that. The whole thing here dates back to 1980. I see some date codes. I think that could be 79. We also have, that's also 79. Maybe some chips have been replaced. I don't know what happened to this thing over this time. But for example, this one is from 80, so I think it's from 1979 or 1980. They certainly built it a couple of years. There's an interface card that goes to our experimental interface playground. There is a difference between the earlier and later series, so you probably have to look which way around it goes. On the other side of this interface card, we have an actual date code, December 16, 1980. So I think we could take that as the birthday of this machine here. I'm a little bit confused. I thought E&L Instruments is a company by its own, but here it's on the same label as Control Data Corporation. So I'm not sure if these two companies belong together somehow, or if they just made a label for this special device here. I don't know. Maybe someone of you knows it. Please write it in the comments if you know it. I'm always happy to read new information. Alright, it's time to turn it on. And as you see, it works. It shows me the address 3000. It shows me some data. I don't know what that is. Maybe some random data that is generated with the power on process. But before I show you how to program this thing, by the way, I found an ad in the internet, an old ad for this MMD-2, and it was about $350 in 1979. That's about $1,200 today. So it was a pretty expensive piece. And I think the case wasn't cheap either. So just look at that, how it looks after all those years. It has two latches here, which have a Velcro on the top that holds it up, so it doesn't get squeezed between the cover, and then we lift that up. And we see some compartments for spare parts or manuals or whatever. And we also have a spare keyboard chip here from a company that was in Zurich. It doesn't exist anymore since a relatively long time. It's a 8279 keyboard and display interface chip. And I have a couple of manuals, some copies that I will need right now. The first program is a simple sample program from the manual. It's just a counter, and that counts up from 0 to 255. It then repeats that and puts the result out to the 3 different output ports. So that is the first command is move B, register B into register A. Then out, this means output that data to address 000, that's port 0. Then output that same number to port 1, output the same number to port 2. Then increment register B. These two commands here, XTHL, is just to slow down the entire process a little bit. I don't know what that command actually does. It swaps some registers somewhere, but it's one of the slowest program steps you can have. It needs 18 clocks for each of the two commands here, and then a simple jump back to 3000. Here it's 4000, but I corrected that because the unit here is always starting at 3000, so I don't have to type the address all the time. So let's see if I can get that a little bit better on camera. Okay, we have the whole keyboard. Now let's start. We start at 3000. The first command is 170. I press the store button, and now 170 is stored at address 3000. Then next, the address counter jumps to 001. The data is 323. Store next. 000, store next. Okay, and I entered all the commands I need. Then I go back to address 0, load it to the lower address. That button is for the higher address bytes. We are at address 3000. The first command is 170, and I simply press go. And as you can see here, we have moving lights. I just see that port 1 is not doing anything, so I probably forgot to program that step. I had a little mix up with the command lines, so I probably simply forgot it. And that's everything it does. It counts binary from 0 to 255, all 8 bits, and then repeats the cycle, starts at 0 again, and does this until the power is cut. Now it's working properly. I just forgot one line with the port 1. I only entered port 0 and 2 address. Now if you want to change the program, for example, I can show you how that is done. It's very simple. First, you have to press the reset button to stop everything and to jump back to the start address 3000. Then, for example, let's say we have a wrong digit in 3010. We can go through all the programs here, or we can enter the low address in the keypad. And let's say it should not be 343, but for example, the no operation code is 000. So if you type a wrong number, just keep typing until the right number is in the display, store, and that's already edited. So for example, if I go one previous, no, next, the other 343, that's the wait cycle, this exchanging of bytes in the registers. I want to have this 0002 and hopefully store that. This should a little bit accelerate the program, because instead of waiting 2 times 18 clock cycles, it now does 2 times the no operation command, and that only uses 4 clock cycles, so it should be a little bit faster than before. I don't know if we see that. We already have 0. We load that as the low address and we say go. Now you can compare by yourself, is it faster or not? Maybe we can find that out with another experiment. I just changed the program a little bit, so we don't only have action here, we also have action over here on the interface board. As you can see, I now also have the output, the same output here on this output port. That's just an additional output port with the address 373. So the command is out 373 if you want to drive these LEDs with any number. Then I have here the analog meter that goes up to 10 and flips back to 0. And if we want to make some noise, I can switch the motor on. That goes together with the analog voltage. And stops when it reaches full speed. Okay, that's enough noise for today. Let's try another thing. By the way, that's the Intel 8080 instruction list here. I don't know if it's complete, I think so, yes. For example, we have here the in and out commands that move data from register A, I think, if I remember correctly, to a certain address. So we have the out command we used in our program. That's the binary code. If you divide this in groups of 3, we have 3, 2, 3. And just think the 0 here. It does not exist, but it's also a number 3 in octal. And that's exactly what we have here. 323 means out to address 0. that's our output register here, number 0. That's that port here, port 0, has address 0, and gets the data from the counter. And so on for port 1, port 2. And I also added the external ports here for the digital analog converter. It's 370. And for this port 373. I think I already told you that, but well, better twice than never. I just typed in a small demo program to show you how the analog section here works. So the program only reads the data here from the AD converter, which is connected to all that stuff here. And then it shows the data over to this output port here. And if I move the potentiometer, we're going up to 255. All LEDs are on, and we can go back to 0 on the other side. Then if I switch that over, we go to the light sensor. We see a certain value here, and if I cover that with my finger, we go back to, well, almost 0. And now it's almost full scale, so I can play with that with the light sensor. Or I take the temperature sensor, that's this one. So if I touch that, it should go higher. Yes, it counts up. Now it's full scale, 255. And now it should cool down. Maybe I heated it up too much with my finger. Maybe I have hot fingers today. Oh yes, now it goes. It starts decreasing. So I think the maximum here is about 30 degrees or something. I heated it up a little bit higher, so it took a while to cool down. And if I touch it again, it counts up. Yeah, that's how that works.